Okay, so I'm going to assume that you have tried to do this example and you filled in the blanks here and come up with the value of the integral and the relative error. So let's take a look at the approach for doing this. So this is our function here. We're going to be integrating square root of x dx from 0 to 4. So f of x is the square root of x, and x itself is going to go from 0 to 4. Now we're partitioning the interval from 0 to 4 using 5 points. So the delta x, the spacing between the points along our partitioned interval, is delta x, and we calculate it as b minus a divided by n minus 1, and it comes out to be just to be 1 unit. Okay, so in this case it comes out to be a convenient number, round number, but it's important to recognize that we're calculating it with this function, because if we were to change this so that it wasn't a convenient number of points, if we had 6 points, for example, then this would not be a rounded number. The method would still work just fine. So here are the values of x that we'll use, and I've just written in here the values of I, where we start at 1 and go through 5. So we've got 5 different points, and we can refer to them with this index I. Okay, so we first determine what our values of x are, and then these values of x go in here and we calculate f of x, and these are the values here. If we were to plot this value square root of x, we would plot this f of x as a function of x. Okay, so in order to solve this, what we're going to do, here is the exact value. It's 2/3 times 4 to the 3/2, and it's 5.333, and so on. The 3's repeat for the exact value. So let's go and work this out for the trapezoid method. Here's the composite method for the trapezoid. We're going to calculate it term by term and put those individual terms here. So the first term is I equals 1. So substituting I equals 1 here, we get this formula. So we're going to evaluate f at x2, which is that point, add it to f at x1, which is that point, multiply it by x2 minus x1, and then divide by 2. So when we do that, we get 0.5. So the first term for I equals 1 is equal to 0.5. Now if we go to the next term, it's going to be I equals 2, and we get this for the formula. And so we'll then use these points to calculate this expression here, and we'll put the result there. That's the result for the second term. And then we repeat this for the next terms. We get I equals 3 and I equals 4, but this is only going to go up to n minus 1, so we're not going to calculate it for I equals 5. So these are the individual terms. We add them up, and this is the integral, and we calculate the relative error, where the exact value is 5.33, and that's the relative error. Okay, so we can repeat this for the midpoint method. Hold on a minute. Okay, for the midpoint method, here is the composite method, and for the first term, it'll be I equals 2. So we substitute I equals 2 in here, and we get this as the expression for the first term. We'll use those 3 points, and we'll calculate the first term here. It's for I equals 2, so it goes there. We don't have a term for I equals 1 or I equals 3, so those are left blank. We're going to then repeat it for I equals 4. That'll be the next term in the series. And when we do that, we get that term there for I equals 4. And that'll be the last term. So for the midpoint method, we only have these 2 terms. We add them up, and we get that value, and we can calculate a relative error shown there. Okay, so for the Simpson method, similar approach. This is the composite Simpson method, and we have a first term where we substitute I equals 1 in here, and that says to use these 3 terms, which would be these terms here, and take that term plus 4 times that term plus that term times delta x, which in this case happens to be 1, and divide by 3. And when we do that, the first term is 1.8047. So then we go for the second term, and that's going to be I equals 3. Substitute it in, and we're going to now use these 3 points, and we calculate out the second term, and we get this value, and those are the only 2 terms that we'll use that we need to calculate for I equals 5. And so we add these 2 terms up, we get this result, and we calculate the relative error. So all of these methods do fairly well. Errors are in the range of a few percent, and we see that the Simpson method in fact does the best. Okay, so that's an example of how you use these methods to integrate a function. We're also going to be interested in using these numerical methods to integrate data. And this is a problem that's shown in your notes, and we discussed it in class. And basically what's going on here is we have measurements of concentration and a volumetric flow rate coming from a pipe as a function of time, and we want to determine the mass recovered as a function of time. So we know that the solution involves solving this integral. The mass at time t1 is equal to the integral from 0 to t1 of the flow rate times the concentration dt. And we can also write this as the integral of m dot, which is the mass rate. Now, we'll assume that these measurements are unevenly spaced in time, and that the measurements at the limits are available. So the trapezoid method will be the most appropriate one to use. And our approach is going to be to basically use this integral here. So we have these data. We're going to first convert these data into a mass rate and get the units right. And then we'll calculate the individual terms from the trapezoid method, just like we did on the previous example. And then we can add up all of those terms to get the mass at the end, or we can sum them sequentially to get the running total of the mass. And that will be what we're after, is to show how the mass accumulates as a function of time. So here are the data. These are the measurements made at this particular day. And you can see it's 1, 2, 3. So there are measurements every day right in the beginning, and then we have day 10 and 14 and 18. So the spacing is somewhat variable here. And this kind of thing is common for these long-term field tests, because sometimes data just can't be taken for various reasons. And so our concentration is shown here in micrograms per liter, and flow in liters per minute. These are typical units for for field data. So what we want to do is calculate the mass rate. And to do that, we want to determine we have to do some conversion. So first thing that I did was to convert from liters per minute to liters per day. And then I can multiply micrograms per liter times liters per day, and then convert to get grams per day. So here's my mass rate in grams per day. And then I can integrate that, or I can determine the individual terms using the trapezoid formula, just like I did on the previous example. And here are the individual terms. And if I sum them, notice that I don't have a term here for the last entry, just like in the previous example. And if I sum them, this is the total mass recovered over these 100 days. And then I can also use this approach to calculate the mass recovered on a daily basis. And what I'm doing here is I recognize that these terms here we can think of as the mass that has accumulated over this time interval, from this time to that time. So these are small increments of mass that accumulate over a particular time interval. So what we can do is to say, well, this is the mass that I've recovered at the start. So this would be 0. And then to get the mass that has been recovered by day 2, I take this mass and I add to it that mass, and I write that sum there. And then the next step would be to take this mass, add to it that mass, and I get that result there, and so on. So each one of these numbers is this number plus that number equals that number. And this gives us a running total of the mass that's recovered. Okay, so here's just a graphical example of how that summation is done, where you take this number, add it to that number, and write that number there. So what I'll do is to show you how this works in Excel. Here is the data that we've just seen, and what I want to do first is to convert it to convert liters per minute to liters per day. So I just take liters per minute, take that cell, and multiply by the number of minutes in a day. And then I can copy this down, and when I do, the cell reference gets incremented, and so there's the data for the flow in liters per day. Now grams per day I get by multiplying liters per day times micrograms per liter times, or divided by 1 million, the number of micrograms per gram. And so that's the mass rate for this particular cell. So it's that number times that number, and then this 10 to the 6th to convert the units. And then I can copy that down, and there's the mass rate for each day. So the terms in the trapezoid, it should be trapezoid method, the first term is calculated here, and it's this is f of x, so it's the average of these two terms, so f4 plus f5 divided by 2 times the difference in that time to that time. Okay, so that's the first term, and we can also copy that down, and we'll copy it down to there. We won't copy it to this last point. Well, let's see what happens if we do. So if we do copy it there, we see we have this negative number, and that's because we click on here, that's because the formula that we've copied is trying to use these cells, which are blank, and so that's not valid. We need to make sure to erase that. So these are the terms in the trapezoid series, and we can add them up. And that gives us the total mass. And if we're integrating grams per day, using days as the variable of integration, then we get grams. So that would be total grams. Okay, we can also calculate what the mass is on a daily basis by starting here with 0 mass, and then the next day would be we would start with the value from the day before, and we would add to it increment of mass that's been recovered, which is in that cell. And then we can copy this down to here. So, for example, right there on day 9, that value is going to be equal to the value from day 8 plus this increment of mass that we get from day 8 to 9. And we copy this down, and here is the final result, which is equal to this total value here. So if we wanted to make a plot of the mass recovered as a function of time, we would plot this column as a function of that column. And if you look in your notes, you'll see plots of the starting data, the concentration, and the flow rate. You'll also see plots of the mass rate as a function of time and the recovered mass as a function of time. So they were calculated using the approach that I just showed you.